Hello and welcome to this Eikon Data API tutorial. My name is Yves. I'm founder and managing partner of the Python Quants. I would start by introducing the topic and giving you an overview of the agenda. The topic is from financial data science, and in particular, we will talk about cross-asset financial analytics, and we will revisit the random walk hypothesis. The agenda in a little bit more detail. We start by reviewing what the random walk hypothesis is all about. We then read historical cross-asset data from the Eikon Data API. I will also show how to easily visualize such data. And we are then moving on to analyze the data based on an ordinary least squares regression approach. I will conclude with a summary. Let me change to the code. All the code is available as a Jupyter notebook, and the Jupyter notebook is self-contained. Everything needed is in there, and the only thing that you need to make sure is that you have either Eikon running on Windows or at least the Eikon proxy running, for example, on a MacBook, which is what I'm using here. The random walk hypothesis basically says that analysis of historical data is of no benefit if you want to make some money in the markets. So the basic idea is that stock markets, and in particular stock prices, or to this and other prices of financial instruments, cannot be predicted, that they are simply random walks, and nobody can predict a random walk. In the same way that nobody can theoretically predict the outcome of such simple games as tossing a coin, for example. A little bit more formally, Michael Jensen in the 70s stated that the market is efficient with respect to an information set S if it is impossible to make economic profits by trading on the basis of information set S. Today we would maybe say, here being in a technical context, that we replace information set S by some data set. And here in Python, it might be a data frame filled with financial data. And this is what we are going to do. This will be one of our first steps to get the data from the Eikon Data API. Once we have the data in there, we can start with the analysis, be it the visualization or then the ordinary least squares regression. Why ordinary least squares regression? Yeah, one of the interpretations of the random walk hypothesis is that the best predictor for tomorrow's stock price in a least square sense is today's stock price, given that the hypothesis holds true. Let me get started by importing the required packages. There is not that much there. Of course, we need the Eikon Python wrapper package, which is called Eikon itself. We import NumPy, we import pandas, and also Cufflinks, which simplifies interactive visualization considerably. Here you see which versions I'm using. All is based on Python 3.6, and you also see the respective versions of the single packages that I'm using. The first, and of course very important step, is to connect to the Eikon Data API. To this end, I'm reading my credentials from a config file, and I set my app ID via ek.setAppID. If the proxy is running in the back end, we should now be able to retrieve data. What we wanted to do is here a cross-asset analysis, and to this end, we will retrieve not too many data sets, but yet kind of number of data sets. Here it is 7 that are listed in the RIGS list object. We start with General Electric stock, Apple stock, the S&P 500, the VIX volatility index, the euro-US dollar exchange rate, the gold price, and also the 10-year Bund price. So it's kind of a diverse spectrum, although we just have 7 different RIGs here specified. But nevertheless, I think we will see that the behavior in terms of the predictability and the random walk hypothesis is pretty similar for all these assets. So Once I have specified these, I can retrieve the historical time series data via ik.getTime series. Here I simply pass the list object with all the RICs. I specify the required fields. I'm just interested in the close prices here, and I define a start date and an end date. So the analysis will be based on data for 2017. So 1 year worth of end of day data, because the bar size is by default daily. I execute this cell, takes a bit, and the first 5 rows now show me the beginning of the data set. And you see we don't have a complete data set, so not for every day we have complete data rows, so to say. When I have a look at the final 5 rows, the same holds true. So in order to avoid any complications in this regard, one of my first steps here is to get rid of all those rows where we have not a number values. When I now have a look at the meta information of the data set, we see that we have the same number of non-null rows for every single RIC that we have data retrieved for. Full data set, although most of the analysis would go through with incomplete data set as well, but here we make sure that we have kind of a complete data set throughout all the different time series. Calculating the log return. So most of statistical analysis are based on returns. I decide here for log returns because typically they are a little bit more easy to handle mathematically. With Python and NumPy in particular here, based on the data frame object, it is kind of efficient because I can calculate the log returns for my complete data set for my 7 columns here in a single line of code. And this yields me yet another row with not a number values, but this is just due to the fact that for this date we don't have any previous reference. The correlation matrix by column, kind of easy to calculate, like many other things when you are working with pandas and the data frame object in particular. We see kind of a typical behavior. We see both positive correlations as well as negative correlations. This is what would be expected given the universe, the small universe of RICs, of symbols that we have retrieved data for. But let us have a look visually at the data. So I'm going to plot the data here. My first line of code here sets the plotting to offline, which means that all the plots that you will see in the following will be rendered locally and not on the Plotly server. But we nevertheless use the engine, the JavaScript engine from Plotly. Single line of code, I normalize the data, call the iPlot method and say I want to have this please as a lines plot. We see now the normalized plot. The single colors are here displayed in the legend, and of course here on the x-axis we have the time shown, like in monthly intervals, more or less, a little bit less here. The frequency distribution, which means the histograms of the log returns, are also easy to visualize. I just change the type of the plot, which means here by the parameter kind to histogram. And for better visibility, I also ask for subplots. So we see now every single column, for every RIC, we now get a subplot with the respective histogram of the log returns. Another interesting visualization approach related to our correlation matrix is the heat map. So here you notice that I first calculate the correlation and then I plot a heat map plot via Cufflinks and Plotly, defining the color scale as blues. And you see here that the darker the blue, the higher the correlation. So when we have a correlation of 1, which holds true for every single instrument with itself, then it's kind of dark blue. The lighter the color, the lighter the blue, going almost to white here, the lower the correlation. Here you see, for example, Apple and GE have a correlation of minus 0.888. Now let us prepare the lagged data. For the analysis to follow, we will work with lagged data. Remember the interpretation of the random walk hypothesis saying that today's price is the best predictor in a least square sense for tomorrow's price. So this implies as well that yesterday's price, or the price from 5 days ago, or the price from 10 days ago, probably doesn't have that much to tell about tomorrow's price. So these are kind of corollaries out of the random walk hypothesis. And to this end now, I will create data frames where I have lagged data, let's say for 1 day, another day, third day, for up to 5 days back. So we are working here with 5 lags, and we will see which lag has the highest weight in ordinary least squares regression. And financially, economically, we would say, well, the higher the weight, the more important this particular lag is for the prediction of tomorrow's price. So here is a little helper function which creates all the lags. So once I've defined my lags and pass to this function a data frame object for a particular rig, then it will create the lags as required. 5 lags, and here now the function comes into play, and for every single rig I do the same thing. It's pretty fast because the data set is not too large. And when I now have a look at the column names for the lags, we see we have lag 1, lag 2, lag 3, lag 4, lag 5. So if we are here today, then lag 1 would be yesterday. This would be the day before, this would be 3 days before, and so forth. The keys in the dictionary are now our lags. So we have our rigs. For every single rig, we now have a separate data frame object. Because we added that many columns, I have separated now the data into single data frame objects. Having a look at the one for the Apple stock, we see exactly how this works. So we have lost a few dates here. So it now starts at the 10th of January. And here we have the price information. And we see this on the 11th of January as lag 1. And we see this as lag 2 on the next day, and so forth. So you see, here is how the lags are created. They are more or less pushed or moved down, one to the right and one down. Let us implement the ordinary least squares regression now. So having the single data frames for every rig available, we will implement the ordinary least squares regression to figure out how important the single lags are based on every single data frame for every single rig. This is what is happening here. I'm iterating again over all the rigs. I'm picking out the respective data frame. I'm implementing on the data frame the regression, and I'm storing the results in another dictionary object. Pretty fast. For these data sizes, Python is really a fast choice here. Having a look at the data set, you see we have now for every rig, we have an ND array object, a list of numbers, so to say, representing the weights from the ordinary least squares regression, the optimal parameters for the single lags. And what can be seen already here is that obviously lag 1 throughout has the highest weight. So ranging from 1.1 to the smallest value here is 0.85. But nevertheless, this is all we can say roughly close to 1. All the other values, on the other hand, are obviously kind of relatively close to 0. But let us have a closer look. A closer look at how this works out in terms of being able to predict tomorrow's prices. I pick out Apple once again, and also the original time series, and now I implement a prediction step relying on the regression results. And when I visualize now a subset of the data, so this is just for 50 days, a smaller subset, What you can see is that the orange line for Apple and the prediction line based on the ordinary squares regression look pretty similar. Similar in the sense they have kind of the same peaks, the same lows, but now comes the difference, shifted mostly by 1 day. So mostly, I mean, not perfectly, but for example, here you see this low is 1 day further. This peak here is seen 1 day later here. So basically, this already illustrates that based on the ordinary squares regression, what we notice is that the prediction values for today are basically the prices from yesterday, and the prediction values for tomorrow are basically the prices from today. So that we here already can see some support for the random walk hypothesis in the least squares version, if you like. But let us go a little bit deeper here by analyzing the results cross-asset, because we have done a cross-asset analysis previously, and we now want to get some insights across the assets. The first thing that I do is I combine the results from the regressions into a single ND array object. When I now take the mean over all the values that we have gathered from the regressions, we see that indeed like 1 gets most of the weight, close to 1, and all the other lags get a weighting of something close to 0. Be it above 0 or below 0, but close to 0. When I put this into a data frame, I have maybe a little bit of a nicer representation, and in particular I can rely on the standard methods of the data frame. So we see here minimum values, maximum values, mean, standard deviation, and all the statistics that one might be interested in at a first glance. Of course, more might be interesting, but here this is kind of convenient to get the summary statistics via a single method call. Let us visualize these results now that we see here as tables. This is also straightforward now that we have the data in the data frame. I call iplot and bar. We now see that the orange bars represent the weight for the first lag and so forth. And of course, also by visual inspection, we see what we have discussed already based on the numbers. The first lag gets most of the weight. We have this nice bar plot based representation here, and there is some variation with regard to the importance here of lags 2 to 5. The mean values can also be illustrated similar to what we did numerically, and this is what we gain from our cross-asset analysis by averaging the results from the ordinary squares regression. Now you might say, well, I see, we knew that, but today's trading place is, so to say, characterized by intradaying much more than by end-of-day data, daily trading, long-term investments. So even if we would not be able to predict data based on end-of-day time series data, we might be able to figure something out intraday. So to this end, we can use the Eikon Data API in the same fashion. Namely, we can replace our end-of-day data by intraday data, and here I will base the following analysis on minute bars. So my previous data set, end-of-day data, now changing to 1 minute bars. Takes a bit. We have the data read in. I do it also for a kind of small time interval. It's just the 8th of January, 2 p.m. to 6 p.m. So it's not a very lengthy interval, but if there might be something in it, we might discover it already in this data set. So here you see also that the data sets are not kind of complete, but I mentioned it before, we can simply go along and work with even incomplete data sets. Pandas helps us a lot in this regard. The data now, as you can see, this is the tail end. We have the last 5 minutes, 56, 57, 58, and 5:59, and the last data point that we have is for 6 p.m. on the 8th of January. So this is now the type of data we work with. The code, on the other hand, doesn't need to change. So we can simply copy here and use the code from before. Pandas takes care, so to say, of the different time interval. When I have now a look after all these steps, first I added the lags here, then I implemented the least squares regression, then I put the results in a data frame. And when I now have a look at it visually, you see the results are not exactly the same, but qualitatively they are mostly the same. So still throughout, what we see is that the first lag is the most important one. Mostly here you can see it like ranging between 0.8 and a little bit above 1 here for the SPX, for the S&P 500. And that the lowest important for the last lag is here discovered for the price of the 10-year bond. And that you see that the lags number 2 and 3 have quite a bit more importance giving the intraday data that we have been analyzing. But be cautious. Of course, we base the analysis here of 4 hours only. There might be some special things going on, some seasonal things, some intraday things in terms of cyclicality and so forth. So I don't want to, so to say, judge or value this. I'm just saying that the numbers change quite a bit from the end of day data. But what remains is that still today's, or the price from this minute, we must now say, is the best predictor for the price in the next minute in a least square sense. This is what we get here, and in particular we get this more or less confirmed when we have a look at the averages. This averages out some special effects here that I pointed out before, and we see without doubt the lag number 1, which is either interpreted throughout here as today's price if you want to predict tomorrow's price, or now in this part it will be the price during this minute is the best predictor for the price in the next minute, or as I said before, for today. Bringing me already to the conclusion section. Based on this tutorial, I think we can safely conclude that it is easy to retrieve historical end of day and intraday data across asset classes via the Eikon Data API, that Plotly and Cufflinks make financial data visualization convenient, and that there is support for the random walk hypothesis based on the ordinary least squares regression analysis. And we can say this is the case both for daily and a little bit less so for intraday. Here in the Jupyter Notebook, you also find links to Eikon Data API developer resources, which I can only recommend that you visit them because they help you get started quickly. And this brings me to the end of today's tutorial. And I see you in the next Eikon Data API tutorial. My name is Yves. I'm founder and managing partner of the Python Quants.